In the last video, we explored this new idea called the instantaneous rate of change. So we were used to what we were calling the average rate of change, which is if you had 2 points on a function, you could take the slope of the line that connects those 2 points. But instantaneous rate of change is talking about how quickly a function is growing at exactly 1 point. And the way we saw that graphically in the last video was that we had 1 point fixed and we had another point moving closer and closer along the curve to that first point. And we wanted to see what the limit of the slope was as the moving point was approaching the fixed point. All right, so what we're going to do now is we're going to sit down in front of a sheet of paper and we're going to calculate this limit algebraically. All right, so let's see what that looks like. So here's the function we were talking about in the last video. It's y equals x squared. Our fixed point here was 2, 4. And I've got this moving point. And so my x value, I'm going to call x. And instead of calling my y value y, I want to put in what y is equal to in terms of x. Can you imagine what I'm going to put in here as the second coordinate? Here's a hint. I know that y is equal to x squared. So this point, if the x value is x, the y value has got to be x squared. Does that make sense? Okay. So now, if we want to take the slope of that line segment there, we're going to need to remember the slope formula. So this, once again, is Algebra 2 stuff. So that slope is y2 minus y1 over x2 minus x1, where those are the coordinates of the 2 endpoints of the line. All right, so here that's going to be x squared minus 4 over x minus 2. All right, so this is the slope of this line segment as x moves around. And in order to form the instantaneous rate of change when x is equal to 2, I want to find the limit of that ratio as x approaches 2. All right, so the number I'm interested to is the limit of this function. All right, so when x is equal to 2, if we just substitute it in, we're going to see that we get 0 over 0. But hopefully this is a style of problem that you are recognizing, that we spent a lot of time practicing this back in Unit 1, because Unit 1 was preparing us for Unit 2. So x squared minus 4, we can factor that expression. It's the difference of 2 squares. So we can factor that as x plus 2 and x minus 2. And so our instantaneous limit, the limit as x approaches 2 of x squared minus 4 over x minus 2 is equal to the limit as x approaches 2 of x plus 2 times x minus 2 over x minus 2. And we can cancel out these two x minus 2's. We can do that because this quantity is not equal to 0 because x is approaching 2, which means x is never equal to 2. We're not interested in what happens when x is equal to 2. Therefore, this quantity is not 0 over 0, so we can cancel it out from the numerator and denominator. So our instantaneous rate of change is equal to the limit as x approaches 2 of x plus 2. Now that we've gotten rid of that 0 over 0 term when we plug 2 in for x, we can plug 2 in for x now. And we get that that's equal to 2 plus 2, which is equal to 4. All right, so as x gets closer and closer to here, the line that's being formed is getting closer and closer to what we might call a tangent line. Okay, similar to a tangent to a circle, a line that only touches a circle in one point. Well, this is a line that's only going to touch this parabola in one point, only at this point 2 comma 4. And what we're seeing is that the slope of that line is equal to 4. If you go back to the big picture video, what we did to solve this kind of casually was we zoomed in on this function super close, and we saw that it approached a line that had a slope of 4. As you zoomed in further and further, this stopped looking like a curved line at the portion we were looking at and started looking like a straight line. And we couldn't tell the difference between that and being a straight line that had a slope of 4. So this kind of gives you an algebraic sense. Now that we know what limits are, we have a much more precise way of being able to talk about this instantaneous rate of change. All right, so this is an important skill to be able to know, calculating an instantaneous rate of change of a function given a specific point of x. So I'm going to want you to be able to do this. And in the next video, we will look at 1 or 2 more examples of this type of function.